Our grasping flexibility is, in part, thanks to diverse strategies. Delving into this, researchers such as Fakes et al. Cataloged an extensive array of grasping strategies, each with its specific application, forming a veritable toolbox of grasps that our hands can facilitate at will, providing a foundation for the adaptability we have showcased. Now, let's talk about robots. Unlike us, they typically depend on a single, pre-programmed strategy and excel in consistently executing it under ideal conditions to accomplish tasks. This approach suffices in a predictable setting. But when unpredictability enters the fray, their limitations become evident. Depending solely on one strategy can limit their ability to adjust their grasps dynamically when confronted with execution errors and uncertainties. These presenting bloopers serve as a humorous reminder of the unique challenges that robots face when it comes to replicating human-level adaptability and improvisation. To bridge this gap, we've devised a novel grasp generation algorithm for robotic hands. Consider it a handbook with diverse strategies imbuing robots with a library of grasping options. Through rigorous testing with a panoply of objects, our algorithm has demonstrated proficiency in executing a broad spectrum of grasps, from the commonly employed power and precision spheres to the more nuanced distal type and palmar grasps. However, grasping is more than just adopting the right strategy. The ability to sense the object being grasped plays a crucial role. In a significant experiment conducted in 1984, it was revealed that when humans have access to tactile feedback, their actions exhibit finesse. Conversely, compromised tactile feedback leads to a less refined grasping process. To illustrate this, we'll apply compound lidocaine cream on the hands for 30 minutes, compromising the tactile sensing. Without the wealth of information provided by tactile feedback, even with diverse strategies, our actions lose their elegance and finesse. In the realm of high-tech robotic hands, despite advancements like the impressive shadow hand, there remains a critical challenge: the integration of full-hand tactile sensing akin to humans. Recognizing this gap, we undertake the task of pushing the boundaries of robotic hand technology and develop our own creation, the F-TAC hand. Unlike its predecessors, our creation is endowed with an unprecedented level of tactile awareness, boasting sensors that cover the entire hand. Equipped with specialized sensors and cutting-edge technology, it can perceive every contour and every texture it encounters with the finesse of a human touch. In contrast, the shadow hand can only perceive the environment through its fingertips, with one-dimensional pressure, limiting its responsiveness to a mere fraction of the interaction. Moreover, when the F-TAC hand makes contact with an object, its fine-grained tactile sensing capabilities transcend the simple identification of binary contact or non-contact. Instead, it intricately captures a wealth of nuanced information concerning the precise location, pressure distribution, and texture of the contact site. Competing with the perceptual acuity of the human sense of touch, the F-TAC hand engages in a delicate exploration and comprehensive understanding of objects, weaving together the intricate details provided by its high-resolution tactile feedback. This innovative hand has the remarkable ability to distinguish not only the surface textures of various materials, but also the subtle forces at play during the interaction. Its sophisticated sensing empowers it to perceive even the slightest shifts in pressure and movement, allowing it to emulate the human tactile experience with exceptional accuracy. By tracking the movements and changes in the orientation of objects in contact, the F-TAC hand sets a new benchmark in the domain of tactile robotics, paving the way for an unprecedented level of interaction. By leveraging a smart mechatronic design, the full-tack hand integrates with tactile sensing capabilities while maintaining exceptional motion capabilities that sufficiently supports human-like grasping. The full-tack hand achieves an extensive range of motion in each degree of freedom and showcases its ability to perform thumb opposition, an important clinical test for assessing proper grasping capability. Additionally, its remarkable dynamic motion is evidenced by the flexible coordination of its fingers. Finally, we demonstrate its versatile workspace by showcasing its ability to grasp objects ranging from a small ping-pong ball to a larger soccer ball. Similar to humans, the full-tack hand can maintain stable grasps with finger impairment. By constantly assessing its environment through full-hand tactile sensing, it seamlessly switches to an alternative strategy, compensating for the impairment and ensuring a stable grasp. Moreover, the full-tack hand possesses the ability to adaptively grasp multiple objects simultaneously. When the golf ball is thrust into the hand, the full-tack hand swiftly identifies its position. Recognizing some grasps for the second object may become impractical due to finger occupations. Instead of insisting on the initial goal, the full-tack hand adapts and chooses a suitable strategy that ensures a plausible grasp on the second object. Experience the captivating finale, as full-tack hand skillfully transports multiple objects to a receptacle. Guided by synthetic grasping strategies, the full-tack hand carefully checks whether its execution follows the plan through full-hand tactile sensing and exploits its hand capacity to grasp as many objects as possible at once, enhancing transportation efficiency just like humans. Even in the face of execution errors, the full-tack hand adapts to complete the transportation task. Watch as it adjusts its approach when it mistakenly grasps the coffee bottle in the wrong position. It foresees the potential collision with the pre-planned grasp of the blue ball. Thus, it reevaluates its hand space and opts to grasp the smaller volume golf ball. By adjusting the following strategies, full-tack hand successfully achieves the transportation task in the same 2 turns.